Around the time you first learned about decimals, a teacher probably told you that 0.999, going on forever, is equal to 1, and you probably nodded and quietly didn't believe it. I didn't. People still argue about it online, for pages, both sides certain. It looks like it's reaching toward 1 without ever arriving. Like there's a tiny bit left over at the end, too small to see, but still there. We're going to take that feeling seriously because it's pointing at something real. And then we're going to find out why the answer is 1 anyway. You've maybe also seen the proof that's supposed to put the argument to bed. It goes like this. 1/3 is 0.3 repeating. Multiply both sides by 3. On the left, 3/3 is just 1. And on the right, 3 times 0.3 repeating is 0.9 repeating. So 1 equals 0.9 repeating. There's a second version that feels even slicker. Call our mystery number x, so x is 0.9 repeating. Multiply it by 10, and you get 9.9 repeating. Now subtract the first line from the second. On the left, 10x minus x leaves 9x. On the right, the endless tails line up and cancel, and all that survives is 9. So 9x is 9, which means x is 1. Both of those win the argument and somehow leave you unconvinced. There's a good reason for that. Look again at the first one. It opens by claiming that 1/3 is exactly 0.3 repeating. But that's the same kind of statement we set out to check in the first place. We quietly assumed a piece of the answer in order to reach the answer. The second proof hides the same move. When we multiplied by 10 and subtracted, we treated an endless string of 9s like an ordinary, well-behaved number, something you can slide over and line up. Whether you're even allowed to do that is exactly what's in question. So we haven't actually settled anything. We've just shuffled the doubt to a different spot. So let's go back behind the tricks, to the symbol itself. What does 0.9 repeating actually mean? A decimal is really a set of instructions. The first 9 says, add 9/10. The next 9 says, add 9/100. Then 9/1000, and on it goes. 0.9 repeating is the instruction to keep adding these pieces forever, with no final step where you put down the pen. Now, we can't sit and add up an endless list. So instead, watch what the running total does as we go. After 1/9, we're sitting at 0.9, and the distance left to 1 is 1/10. Add a second 9, and we're at 0.99, with 1/100th still to go. After the third, the gap is down to 1/1000th. Every 9 we tack on shrinks the leftover by a factor of 10. After n 9s, the gap to 1 is 1/10 to the power n. That sliver you felt at the start is real. At every stop along the way, it is genuinely there. Here's the move that does the real work. Pick a gap, any gap you like, so long as it's bigger than 0. Say 1/1000th. By the fourth 9, the leftover is already smaller than that. Fine, you say, and you reach for something tinier, a billionth. We slip under that one by the 10th 9, so pick the smallest positive number you can be bothered to write, with 100 zeros after the point. The 9s drop below it before you finished writing the zeros. Whatever gap you name, the running total eventually gets nearer to 1 than that. There is no positive distance that the 9s fail to beat. And there's the secret, sitting in the open. We never finish adding the 9s, so 0.9 repeating can't mean the final total in the list. There is no final total. It has to mean something steadier. It means the one number the totals are closing in on, the single value with no daylight left between it and the sum. And we've just shown that the only number with no positive gap to the 9s is 1. This time, there's no sleight of hand. 1 is simply the only number that fits. Everything else, even a value a hair below 1, gets overtaken and left behind. 1 is the one spot that never gets crossed. That is what the symbol has been pointing at the whole time. But hold on, you might say. Maybe they're not equal. Maybe 0.9 repeating just sits infinitely close to 1, a hair short, with the tiniest possible gap between them. It's the most natural objection there is, so let's take it seriously. Suppose there really is a gap. Call it size d and say it's a real number bigger than 0. Here it is, some fixed positive distance below 1. Here's the trouble. On the ordinary number line, there's a rule. Name any positive number, and you can always find a fraction, 1 over n, that is smaller still. Halve it, then halve again. 1 over 1,000, 1 over a billion. The fractions march straight past your d, heading for 0. So your fixed gap d cannot be the smallest positive number because there is always a smaller one sitting underneath it. The only distance nothing can slip beneath is 0 itself. Numbers that small, infinitely small, do exist in other systems mathematicians have built. But the everyday real numbers are not one of them, and 0.9 repeating is an everyday real. So the gap is exactly 0. Now back to that stubborn feeling, the little bit left over. Where does it actually come from? It comes from secretly imagining that the 9s stop. You picture them ending somewhere, at a last 9, with a final crumb of a gap sitting after it. And if they did stop, you'd be completely right. There would be a gap. But there is no last 9. Go and hunt for it. Whatever 9 you point to, there's another one already behind it, and another, with no end to arrive at. The leftover sliver lives at every place where you quit early. 0.9 repeating is the one object that never quits early. So the spot where the sliver would sit is a spot the number simply never visits. This discomfort isn't new, and it isn't a sign that you're bad at maths. For a very long stretch of history, serious mathematicians refused to touch endless sums at all. Zeno used this very idea to argue that a runner can never finish a race. First, he has to cover half the track, then half of what remains, then half of that, on and on without end. It took centuries to grow comfortable with the thought that an endless process can still have a single, finite destination. The way out was to stop asking what happens at the end and start asking what the steps are heading toward. So here is where we land. Name any gap at all between 0.9 repeating and 1. Go ahead. The 9s will swallow it. There's no room left to fit even the thinnest difference you could dream up. And when there is no difference between two things, anywhere, by any amount, then they were never two things to begin with. 0.9 repeating and 1 are two names for a single point. The same place on the line. The same dot. The shortcut just told you that the dot was there. The long way is how you get to stand on it.